Well, students, here we will discuss about the refraction through a prism, and in the last section we have discussed about how the refraction occurs, and in refraction, the phenomenon of refraction of light, we have derived different relations and how the refraction through a lens occurs, and through a convex refracting surface and through a concave refracting surface, that we have discussed. But in this section we will discuss the refraction through a prism, and when this refraction occurs through a prism, what phenomena, what involved in that refraction. So before we start the refraction through a prism, first of all we should know that what is a prism. What is a prism? If I will ask you, what do you mean by, or what is a prism? So you can say that a prism is a homogeneous transparent refracting medium. A prism is a homogeneous transparent refracting medium. Homogeneous transparent refracting medium, like your glass. It is a refracting medium, transparent refracting medium, bounded by two non-parallel plane surfaces. Non-parallel plane surfaces. Non-parallel plane surfaces. Two non-parallel plane surfaces. And these surfaces, these non-parallel plane surfaces, inclined. They inclined at some angle. Inclined at some angle. Clear? A prism is a homogeneous transparent refracting medium bounded by two non-parallel plane surfaces inclined at some angle. So if I show that for a prism, let me draw like this for a prism, right? Then this is the portion okay. This I can say is a prism. Clear? And let me draw like this, or we can show. Clear? And this is a prism. And here in this case, there are 1 point, one surfaces like that. So there are two refracting surfaces. One is on this side, the other is on the other side. Two refracting surfaces. And these surfaces are called refracting because the light ray enters and emerges from these two faces. These are called refracting faces. And this portion is called as the base of the prism. This portion is called as the base of the prism. Clear? And okay, I will show that this is a straight line. Actually, this is a straight line, so it will be more clear. Like this, and we can join like this. Clear? That's straight line. So this is like a prism, and the two non-parallel faces. These are the two non-parallel faces. The two non-parallel faces like this. Non-parallel forces inclined at some angle, and this portion, and in this region some refracting medium is there. In this portion some refracting medium, and this one is called as the base of the prism. This is called as the base of the prism. So I can show that this portion is the base of the prism, and these surfaces are called as the refracting surfaces. Two surfaces, refracting surfaces. Light enters and emerges. And the angle between these two refracting surfaces, the angle or the incline between the two refracting, one is this side, the other is this side surface, this angle is called as the angle of prism. Angle of prism. And generally the angle of prism is shown as a capital A. Generally we can show that it's a capital A. This is the angle of prism. And this is the refracting surface. And this portion is called as the base. Okay? And in the prism case, any section of the prism caught by a plane perpendicular to the refracting faces. Okay? Perpendicular to the refracting faces or edge. Any plane, we can say that any section of the prism caught by a plane. Any section of the prism caught by a plane perpendicular to the refracting faces is called as the principal section. So if I show that principal section, let P, Q, R. I caught like this edge. At this edge I will caught like this perpendicular to the refracting surface. Then it will show that this is called as the principal section. P, Q, R. This one is called as the principal section of the prism. Principal section of the prism. So these are the terms associated with a prism. There are two refracting surfaces, one base and one angle of the prism. Okay, or that is also called as the angle of prism, or that is also called as the refracting angle. That is also called as the refracting angle. Clear? Now with this knowledge, we will go for the refraction through a prism. Now let us go for the refraction through the prism. Let me show the principal section of a prism. Let me show the principal section of a prism like this. So this is the principal section of a prism, and let me name this as a, or I can name it like that. This is the angular prism, so we can take A, B, C is the principal section of the prism, where A is the angle of the prism. This is the refracting surface, this is another refracting surface, and this is the base. And I have called that perpendicular with a plane perpendicular to the edge, principal section edge. So that is the principal section, right? Now with this, how the refraction occurs through a prism. Now this is a air medium, this is some refracting medium like your glass, transparent refracting medium, and this is air. Let us consider the A enters through one of the refracting face like this, and let a ray enters with an angle of incidence I at the incident ray on the face, refracting face AT, and this is the normal to the refracting surface AB. And this is an incident ray enter. Incident on the face AB. So obviously, normal with the incident ray, this is called as the angle of incidence I. Now the ray gets refracted from rarer to denser. So it bends towards the normal. If there is no refraction, there is no medium, the ray will go along this path like. Clear? This ray will go undeviated, rectilinear propagation. But because of this prism medium, the ray travels from air medium to glass or air to denser. It bends towards the normal. Now the ray will travel along this path. Clear? So I will show the path is bends towards the normal. So let the ray travels like this towards the normal. Clear? So at this phase, when it strikes the phase AC, then at this phase again what happened? If I draw a normal at this phase again, let me draw a normal at this point of incident on the phase AC. Like this, I draw a normal like this, and this is the normal here. This is the normal. So if this is the refracted ray, then I can show that if this is the angle of incidence, this is the angle of refraction because the ray is refracted. So let this angle of refraction R1. This angle of refraction is R1. And after refraction, the ray travels. Let me name it. This is suppose PQ is the incident ray, and R is the refracted ray and incident at this phase AC. Let the angle of incidence here is suppose R2. Let me take the incident ray as R2. Incident at which phase? AC. After incident, the ray now travels from denser to rarer. So obviously it bends away from the normal. So the emergent ray will bend away from the normal. This is the normal. So it bends like this away from the normal. Then obviously if this is the emergent ray, we can take this angle. The emergent ray makes with the normal. That we can take as the angle of emergent E. Angle of emergent E. So because of this refraction, this is the PQ is an incident ray and QR is refracted to the prism and RS is the emergent ray. This emergent ray now, because of this prism, the emergent ray deviates from the incident ray. Deviates from the incident ray with some angle like this. How much it deviates? This much is the deviation. So this angle is called as the angle of deviation delta. Clear? This is called angle of deviation delta. Right? And let me name this one as, this is your M suppose and this is your N. And this is the angle of prism A. Clear? This is the refraction through a prism. Refraction through a prism. Now this delta is called angle of deviation. What is this angle of deviation? The emergent ray makes with the line of action of the incident ray. So this PQ is incident ray is like this one, but it emerges like here. It makes an angle delta. Remember, this delta is very, very important. The angle of deviation is very, very important. Now if I show the angles like this, then if I show what is this angle, if this is I, what about this angle? This is I means this total angle will be I, but this is R1, I have taken R1. So this must be I minus R1. And what about this one? This must be E minus R2. E minus R2. Clear? So this is the naming of the all the ray diagram for refraction through a prism. Now we will find the angle of deviation. I will find an expression for this angle of deviation delta. Clear? So how we find this angle of deviation delta and expression for this angle of deviation delta. Right? Now you see the case like here. What is this? Delta is equal to, I can write, what I can write this delta? In the triangle NUR. In the triangle in the triangle NQR. See the triangle NQR. Delta is an external angle that should be sum of interior I minus R1, one angle, plus E minus R2, this angle. This plus this equal to external angle. Or delta is equal to I plus E minus R1 plus R2. Let me write this as equation 1. That is the angle of deviation delta. Clear? So I got the expression for delta. Then if I make it more simplified, for the expression delta, if I make it more simplified, how to make it the more simplification? I will write this in angle of prism, in the form of angle of prism. How to write this one, this expression? In the quadrilateral, AQMR, in the quadrilateral AQMR, I can write the angles are like this. This first I write RAQ plus angle AQM plus angle, see the figure, QMR plus angle MRA is equal to 360 degree. Sum of four angles of a quadrilateral is 360 degree. Now in this case, what is this RAQ? RAQ, that is simply I will take is the angle of prism A. Notation for this is the angle of prism plus angle AQM. This is a normal, this AQM, this is a perpendicular, so this is 90 plus QMR, let me keep like this, QMR plus what is this MRA, again 90, is equal to 360 degree. Or I can write angle of the prism plus QMR is equal to 180 degree. 90, 180 minus this side 180 degree. So this is equation number 2. Next, in the triangle, now go to the triangle QMR, the sum of these three angles R1, R2 plus QMR is 180. So I can write directly R1 plus R2 plus angle QMR is equal to sum of the three angles is 180. Now this is equation number 3. Comparing equation 2 and 3. Comparing equations 2 and 3. Now compare this 2 and 3. QMR get same. So A should be equal to R1 plus R2. So let this is equation number 4. A is equal to means the angle of prism is equal to, A is what? Angle of prism is equal to R1 plus R2. R1 is the angle of refraction on the face AB. R2 is the angle of incidence on the face AC. A is equal to this one. And this is always true for a prism. Next case. Okay. Putting equation 4 in equation 1. What is that equation 1? Delta is equal to I plus E minus R1 plus R2. That is equation 1. If we put equation 4 in equation 1, what is R1 plus R2? That is the A. Or I can write I plus E is equal to A plus delta. Equation number 5. And this is a very important relation in the deviation or deviation produced by a prism. Now you see this expression. I plus E is equal to A plus delta. If you see this one, we can say the angle of incidence plus the angle of emergence equal to angle of the prism plus angle of deviation. Plus the angle of deviation. And what the equation again says, this, by using this equation, we can derive the refractive index of the material of the prism by using this equation. And also we will get so many relations by using this equation. Now what is the significance of this one? The angle of, we can say that when a ray of light is refracted through a prism, the sum of the angle of incidence and the sum of the angle of incidence and the emergence angle is equal to, emergence angle is equal to angle of the prism plus the sum of angle of prism and angle of deviation, and the angle of deviation. Now next we will go for the angle of minimum deviation. What is this angle of minimum deviation? What is this angle of minimum deviation? You see, if we plot a graph between angle of incidence and angle of deviation, we get what is the nature? If we plot a graph, now you see here, I will take the angle of incidence on this side and angle of deviation delta. For different angle of incidence, you will get different delta. But first what you will observe that when the angle of incidence increases, the angle of deviation decreases. The angle of deviation decreases. And it attains a minimum value. It attains a minimum value like this. It attains a minimum, lowest value. Then after that, if you increase the angle of incidence, you will get a increase in angle of deviation. This is the nature of the graph for I versus delta. And this value is called as the angle of minimum deviation. Angle of minimum deviation. Angle of minimum deviation delta m. This angle is called angle of minimum deviation delta m. So what again this graph shows, now you see here. Let me show a point that for the same delta angle, let me plot like a straight line like this. For the same delta value, we will get two angle of incidence I1 and I2. Means for two angle of incidence, you can draw the line anywhere. For two angle of incidence, one is I1 and I2, we will get two angle of deviation. Sorry, the same angle of deviation. For two different angle of incidence, we will get one angle of deviation. But for this value only, for this value, we will get for one angle of incidence, we will get one deviation angle, that is your delta m. And that's why it is called as the angle of minimum deviation. At this point, you will get only one angle of incidence. For that, the angle of deviation, that angle of deviation is called as the angle of minimum deviation. Clear? So this is the discussion. And again in this discussion, when this angle of deviation reaches, then at angle of deviation, at angle of minimum deviation, what happens? At angle of minimum deviation, we can write at angle of minimum deviation, that is delta is equal to delta m. We have, remember always, when delta is equal to delta m, this delta is equal to minimum deviation for a prism. When this occurs at angle of minimum deviation, delta is delta m, we have angle of incidence equal to angle of emergent. Angle of incidence is equal to angle of emergent. I is equal to E. If I is equal to E, and if I is equal to E, then what? R1 should be equal to R2. R1 should be equal to R2. And this is a very, very important concept. At the angle of minimum deviation, delta equal to delta m, we have I is equal to E, angle of incidence equal to angle of emergent, and R1 is equal to R2. Clear? So this is the expression. Now, in this case, in the position of minimum deviation, what happens actually? The prism lies In this angle of minimum deviation case, another thing is that in this position means at minimum deviation case, in the position of minimum deviation, in the position of minimum deviation, in the position of minimum deviation, in the position of minimum deviation means when this minimum deviation occurs for a position, the prism lies symmetrical. The prism lies symmetrical with respect to the prism lies symmetrically with respect to the what? Incident ray and the emergent ray. With respect to incident ray and emergent ray. Symmetric with respect to incident ray and emergent ray. That is I is equal to A. What it means? Simple language is that when this delta is equal to delta M, then I is equal to this angle should be equal to this angle, and the prism is symmetric both incident and emergent. If I is equal to A, then obviously R1 is equal to R2. And at this position, the prism lies symmetrically with respect to incident ray and emergent ray. Means symmetrical means you can say that this red line, the refracted ray in the prism, inside the prism, is parallel to the base of the prism. These two rays are parallel. Means we can say the refracted ray inside the prism is parallel to base of the prism. Clear? So at the angle of minimum deviation, this occurs. And remember, this is the case. Now you can ask, when delta equal to delta M, how can we show that I is equal to E mathematically? This is graphical method. Graphically we have shown this one. How mathematically I will show that. That also you should know. Let me erase this thing and let me show that mathematically when delta equal to delta M, I is equal to E and R1 is equal to R2. Let me show that mathematically. So let me show that mathematically. We have, this is for your understanding. You can show for in long question. If it is a long question, then you no need to write this mathematics. Only you can show by a graph. But for mathematics we have I plus E is equal to A plus delta, or I can write delta is equal to I plus E minus A. I can write this delta is equal to, let me write, root over I whole square plus root over E whole square minus 2 into root over I into root over E, clear, plus 2 into root over I into root over E minus A. Can you write? Root over I whole square, this is I, root over E whole square, this is E, minus plus. The same thing is minus, the same thing is plus. So this is 0. Minus A as it is. Right? Or I can write this delta is equal to, let me write this one, root over I minus root over E whole square plus 2 into root over E minus A. Now you see this expression. I need this delta should be minimum. So then delta is equal to delta M. Let that is the minimum deviation. At minimum deviation, if this delta is reduced to delta M, what will be the minimum value of delta M? The minimum value of delta M, I can say that the minimum value means this can be taken as 0 because this is a negative of 2 terms, minus of 2 terms. You can make this 0. But you cannot make this 0 and you cannot make this 0 because this is the product of two things, angle of incidence, angle of emergence. They cannot be 0. Angle of the prism cannot be 0. If the prism exists, it has the angle of prism. And this I, if an incident ray, there is an angle of incidence and there is an emergent angle. So they are negative, they never be but 0, this one never be 0. But this can be 0 because this is a subtraction of two terms. So when delta is equal to delta m, I can say root over I minus root over e whole square is equal to 0, or root over I minus root over e is equal to 0, or root over I is equal to root over e, or I is equal to e. So at delta equal to delta m, I is equal to e. If I is equal to e, then R1 should be equal to R2. So R1 should be equal to R2. That is the proof mathematically. Clear? After getting this angle of deviations case, now let me find the refractive index of the material of the prism. What is the refractive index of the material of this prism? Let me find. Refractive index, same refractive index of the material of the prism, of the material of prism. What is the refractive index of material of prism? Let me find by that using that expression. So we have using the Snell's law, Snell's law for refraction at the face AB. Use the Snell's law. What the Snell's law gives you? If you take the refraction using the Snell's law, what you will get? The refractive index of this medium, because this is the refracted ray, this is the incident ray. Refractive index of, let me write, glass medium, this is made of glass, with respect to air, or simply I can write this as the mu, absolute refractive index of this medium, because this I consider air. So absolute refractive index is equal to sin I by sin R1. Sin I by sin R1. Clear? Now, what is the sin R1? How will we find the sin and the R1? So, for a prism, use the formula I plus E is equal to A plus delta. I plus E is equal to A plus delta. And R1 plus R2 is equal to A, angle of the prism. That already you know. But if delta is equal to delta M at minimum deviation, I is equal to E and R1 is equal to R2. Now put here, I can write this as 2I is equal to A plus delta M. 2I is equal to A plus, then delta equal to delta M, or I is equal to A plus delta M by 2. First case, I got I. Then here, now you put R1 in place of R2, I will put 2R1 is equal to A, or R1 is equal to A by 2. Yes? So let me put this is equation number 6. Let me take this as 7 and 8. Putting 7 and 8 in equation 6. Putting 7 and 8 in equation 6. If you put that, putting 7 and 8, putting equations 7 and 8 in equation 6, what I will get? The absolute refractive index of the material of the prism is equal to sin, what is I? A plus delta M by 2 divided by sin R1. What is this R1? A by 2. So this is the required formula for refractive index of the material of the prism. Okay, this is the expression for refractive index of the material of the prism. And from here we got the difference. Then this is the required formula. And remember, from the beginning, from the refraction through a prism up to this, it is a long question. It is a long question. Derive an expression for refractive index of the material of prism. When the refraction occurs through a prism with angle of prism is A and angle of deviation is delta, derive the expression. So we will derive this one. Clear? Now, for a thin prism, or small angle prism, What means small angle prism? This angle of prism A is very small. That is a thin prism. Right? Like of the order of 6 degree. Up to order of 6 degree. Then for small angle prism, we can write this sin A plus delta m by 2 is equal to sin theta is equal to theta. Sin theta is equal to theta and sin A by 2 is equal to simply A by 2. Sin A by 2 for small angle prism. Clear? Then means what? For small angle, sin theta equal to theta, sin A by 2. A is small also. This A is small. The A is small, since delta is also small. Angle of minimum deviation is small. So sin theta equal to theta. Then if you put that, mu is equal to A plus delta m by 2 divided by A by 2. That is your mu. Clear? Or I can write this is equal to mu. Or I can write mu is equal to A by 2 divided by A by 2 plus delta m by 2. Here A by 2 plus delta m by, okay, let me write like this, then it is more clear. This is A by 2. So now I cancel this 2. Then mu is equal to, I can write A plus delta m by A, or mu is equal to 1 A by A 1 plus delta m by A. Or I can write this as 1 plus delta m, right? So A by A is 1 plus delta m by A. Okay? Or I can write this as, okay, so no need to take this one. Let me write here also. If A plus delta m is equal to A into mu. Or I will write A into mu minus 1 is equal to delta m. A minus this side, A mu minus A is equal to delta m, or take common A, mu minus 1 equal to delta m. This is an expression for small angle prism. This angle of deviation is equal to angle of prism into refractive index minus 1. This is also a relation. And this relation, when you see this relation, the angle of minimum deviation is what? The angle of deviation produced by a thin prism does not depend on what? The angle of incidence. It does not involve any angle of incidence. So the angle of deviation by a small prism does not depend on angle of incidence, right? And but it is a what? It is a constant quantity for a given prism. This deviation angle is a constant quantity for a prism, because for a prism this A is constant and mu is constant. So it is a constant. It does not depend on at what angle the range instant for a small angle prism. And a thin prism gives less deviation of light. A thin prism gives less deviation of light. Clear? By that also you can derive this relation by using another way. Another way we will find the angle of deviation for a small angle prism. I will derive that expression what I have derived right now for thin prism, that I will derive again in another way. Deviation through a prism of small angle. So as you know, let us consider the principal section of the prism, right? And this is a normal, this is another normal on this face. This is an incident ray with angle of incidence I. This is refracted inside the prism. This is suppose your angle of refraction R1. This is the angle of incidence on this face R2. This is your R2, and this is the emergent ray, and this is the angle of emergent. Okay? This is the case like your refraction through a prism. And this angle of deviation, you can show that this is the incident ray and this is the emergent ray. This angle is called angle of deviation delta. That already you know that. Now for this one, let me consider this is the medium 2 and this is medium 1, this is medium 1. For refraction at the face, let me give the name ABC. For refraction at the face AB, using Snell's law, refracting index of two material of the prism with respect to air medium, glass with respect to air, or 2 with respect to 1 is equal to sin I by sin R1. For small angle prism, for a prism of small angle, I and R1 also small. Angle of incidence and angle of refraction also small. So I can write for small angle, I can write directly mu21 is equal to I by R1. I by R1. Or this implies I is equal to mu21 into R1. Let this is equation 1. Similarly, for refraction at the face AC, what I write here? Refracting index of 1 with respect to ray 2. The ray is traveling from 2 to 1. So 1 with respect to 2 is equal to sin incident angle is what? R2 by sin E. For small angle, for a prism of small angle, for a prism of small angle, R2 and E also small. If A is small, IE, R1, R2, E all are small and delta is also small. So I can write this as directly mu1 2 is equal to, or I can write this mu1 2 is equal to R2 by E, or mu1 2 according to principle of reversibility, right? mu21 is equal to, what I can write? 1 by mu1 2. Principle of reversibility, mu21 is equal to 1 by mu1 2, that equal to 1 by this, means E by R2. Or I can write this as this is equal to E is equal to, here E is equal to mu21, E is equal to mu21 R2. This is equation number 2. This is equation number 2. Then we will go to the relation. We have I plus E. We have for a prism, deviation through a prism, I plus E is equal to A plus delta. Clear? What is this I? Mu21 R1 plus what is E? Mu21 R2. Mu21 R2 is equal to A plus delta. Or you can write this equal to, take mu21 R1 plus R2 is equal to A plus delta. What is this R1 plus R2 for a prism? Angle of prism plus A is equal to, this is equal to A plus delta. Or you could take A common this side, mu21 minus 1 is equal to delta. This is the relation. Like the refractiveness of the material of prism. So it does not depend on angle of incidence. It only depends on angle of prism and refractive index. So you can say for small angle prism or a thin prism, this is a constant. Angle of deviation is a constant. Okay. Then next we will go for another phenomena observed through a prism. What is that? Dispersion of light through a prism. So already we discussed about how the refraction occurs through a prism and what is the refractive index of the material of the prism. Then for a small angled prism, angle of deviation delta depends on what are the factors. Now next is the dispersion of light through a prism. That is also a phenomena observed through a prism. It is common to all, and we are observing in our day-to-day like that. When you take a prism, allow to pass the white light through the prism, you will get, after the light pass through the prism, on the other refracting surface, we will get different colors. Like here, what are the colors? 7 colors. We will observe the 7 colors on other side, and if you place a screen, we will get the 7 colors. That is called as the spectrum. We will find the spectrum of light. Clear? So this dispersion is what? It is the phenomenon of splitting of polychromatic light. Polychromatic light. What is polychromatic light? Polychromatic. The light consists of more than one wavelength. That is called polychromatic. If it consists one wavelength, monochromatic. So it is the phenomenon of splitting of polychromatic light. Like your example is your white light. We can say it consists of 7 wavelengths. So that's why you are getting 7 colors. Of splitting of polychromatic light, then the splitting of polychromatic light when it is the phenomenon of splitting of polychromatic light into its constituent colors, when passes through the prism, when passes through a prism. Clear? It is the phenomenon of splitting of polychromatic light, right? It is a phenomenon of splitting of polychromatic light into its constituent colors when passes through a prism, or you can say when it passes through a refracting medium. When passes through a prism is an example, you can say when passes through a transparent refracting medium. The example is your prism, right? So means what happens? If there is no prism, if you allow the white light, it consists of 7 colors, but the dispersion is not occurring. But when it passes through the prism, you will get the constituent colors. How this will you can show that? Let us consider this is the principal section of the prism. There are the 2 refracting surfaces, this and this, and let a white light pass like this. If there is no dispersion, it will go along this path like that without any deviation, the rectangle linear, no refraction, it goes like this. But because of the refraction, you will get the 7 colors like that. The 7 colors, then you will find the 7 colors like that. 1, 2, I am showing all are same colors, but you will get the 7 colors like that. The 7 colors are not available here, so I can show like this, and you are getting the 7 colors like this. 1, right? The others are, you can show like this one by one. You can show like that, the colors are like this. Like that you will get the 7 colors. And what the range is like? So you will find that they are violet, then indigo, next blue, then green, then yellow, then orange, then you will get the blue color. Then you will get the red color. This is the red. B, G, Y, O, R. These are the 7 colors. So this is the white light, and this is called as when you place this is called as the spectrum of light. The constituent colors. So that occurs. So when you see that in the red color is at the top and the violet color at the bottom. And as you know, the red light has the larger wavelength than the violet, and all are in the sequences like this. Right? This is smaller, then this is larger than this one. Blue is larger than indigo, green is larger than blue, yellow is larger than green, orange is larger than yellow, red is larger than all wavelengths, right? So the thing is that now you comes in your mind that what actually happens. This happens is what is how this splitting or why this splitting occurs. The cause of dispersion. Now we say that what is the cause of this dispersion? Cause of dispersion. Why it splits? Cause of dispersion. What is the cause of dispersion? The simple logic is that you will get the constituent colors means if this is the white light, if the white light after refraction will come as a white light, then you will say that all the wavelengths are on the same white light, but they are deviated through different angles. Means if we say here, this is the red case, this red has a deviation, suppose this is the delta R, and for this violet it has a deviation like this, delta B. This is a deviation like here, delta B. Means the angle of deviation, this is the incident ray, the angle of deviation are different for different color. Then it passes through the prism. Why this happens? The angle of deviation is different, so that we are getting different colors. Why this happens? Now as you know that according to Cauchy's formula, there is a Cauchy's formula. According to Cauchy's formula, what this Cauchy's formula says, the refractive index of the material is A plus B by lambda square plus C by lambda 4 plus like that. Means the refractive index of the material of a prism or a refracting medium depends on the wavelength of light passes through that medium. How it depends? Like that. And A, B, C are the constants. Okay? Are constant. The value of which depend on the nature of the material. A, B, C are constant. Depends on nature of the material. Here the nature of the material of the prism. So we are not discussing about this ABC. But the refractive index is inversely proportional to lambda square. But if we neglect this higher power, suppose you say this to up to this dot, refractive index is inversely proportional to lambda square. Clear? So we can say that from here you can write the refractive index, from this case, from this expression, the refractive index is inversely proportional to, I can say, lambda square, lambda 4, like that. Means larger is the wavelength, smaller is the refractive index. H for white light case, we are discussing for white light. H, the wavelength of red light is greater than the wavelength of violet color. I am taking the two extreme colors of the 7 colors in the white light. The wavelength of red light is greater than the wavelength of violet. If we use this one, if lambda r is greater than lambda v, then the refractive index of the material of the prism for red light should be less than the refractive index of the material of the same prism for violet light. And how they are? The refractive index of the material of the prism for red light is less than the refractive index of the material of the prism for violet light, because as you know, the wavelength of red light is greater than the wavelength of violet light. Clear? This part is over, right? So the refractive index is less than. Now, as you know, the angle of deviation of the expression for angle of deviation, if you recall, the angle of deviation delta, the formula is mu minus 1 into A for a small angle prism. The angle of deviation delta for a small angle prism depends on the refractive index. And the angle of prism, obviously this is a constant, so these are the constant. But if you use this one, as you know, this delta proportional to, or means delta increases with mu. So whose mu value is larger, for it the delta value will be larger, because delta x, or we can say for the angular deviation for red light means refractive index for red light minus 1 into A. Similarly, the angular deviation for violet color, refractive index for violet minus 1 into A. But as according to this one, as mu r less than mu v, so angle of deviation for red light is less than the angle of deviation for violet light. So the different angle of deviation for the, so red light is at the top and violet is at the bottom. They deviate like that. So for red light, this is the angle of deviation. For violet color, this is the angle of deviation. You are getting different. And all the colors in between them, they get different angle of deviations. Clear? So this is the cause of your what? The dispersion of light. Clear? Is that clear? So this is the cause for dispersion, right? So means the red color deviates less or least, violet color deviates most. So from here, violet color deviates most or more, and red color deviates least. These are, and the other colors are in between the red and the violet. So this is the reason for dispersion, and why this dispersion occurs, the reason for dispersion, and what is the dispersion of light. Okay. Next, another definition associated with the prism, angular dispersion. Now we got the cause of dispersion, and what is this angular dispersion? Now I show a ray diagram. White light incident, as you know, the angle of deviation for red light delta r, and for yellow light I have taken delta, and for violet color it is delta b. These are the angular, or these are the what? The angle of deviations for different colors. As you know, red light is at the top, and violet is deviates most, red light least. That already you know that. From here we got the definition of angular dispersion. It is defined as the difference in the deviation. Difference in the deviation. It is the difference in the deviation. Difference in the deviations suffered by two extreme colors. What are the extreme colors? Red and violet. They are two extreme, right? This is the suffered difference is the deviations, difference in the deviation suffered by two extreme colors when passing through a prism. In passing through a prism. In passing through a prism. Passing through a prism. And what the extreme colors? Red and violet. So means angular dispersion generally is shown as theta. So I can say theta is equal to difference in the deviations. So which is more? Delta V for violet minus delta R. Theta is equal to delta V minus delta R. Now you can find the expression for theta in terms of refractive index. As you know, delta V, angular deviation of violet, for small angle prism, the formula is refractive index for violet minus 1 into A, angular prism. For red light, mu refractive index for red minus 1 into A. So theta is equal to delta V, mu V minus 1 into A minus mu R minus 1 into A. So this equal to mu V minus 1, then minus mu R minus plus 1 into A. So plus minus 1 gets cancelled. So theta, the angular dispersion theta is equal to, I can write mu V minus mu R into A. So this is the expression for angular dispersion. This is the expression for angular dispersion. And its unit is a degree or radian. Like your angle, unit is a degree or radian. Clear? So this is the expression for angular dispersion. Clear? So this angular dispersion is equal to, for two extreme colors, for white light, refractive index for violet minus refractive index for red into angle of the prism. Clear? So this is the angular dispersion, right? And it depends on the angle of the prism and the nature of the material of the prism. Clear? Next, another definition is dispersive power. What is this dispersive power? So what is this dispersive power? The ability of the material of the prism, to disperse, to split the constituent colors, right? So this we can say that it is the ability of the material of the prism, ability of the material of the prism to disperse, ability of the material of the prism to disperse the constituent colors of incident light. Prism to disperse the constituent colors of incident light. White light is incident light and the constituent colors are the 7 colors. Okay, constituent colors of incident light. So it is the measure, or it is the ability of the material of the prism. What material it is the, so how much it will deviate the rays and how it will measure that. That can be measured by a mathematical formula is that. So it is the mathematical formula which is given as the dispersive power is the angular dispersion to the mean deviation. It is the ratio of dispersive power is equal to the ratio of angular dispersion to the mean deviation. Angular dispersive power is the ratio of angular dispersion that already you know about angular dispersion. Now you read that angular dispersion. So angular dispersion to the mean deviation. That mean deviation we will discuss here. What this mean deviation means? Angular dispersion to the mean deviation. So we can show that the angular dispersion theta, suppose the mean deviation is suppose delta. So as you know theta for white light case, that is the theta is what? Delta V minus delta R. Delta V minus delta R. That is the angular dispersion in terms of what? Angle of deviation divided by delta. Then what is this mean deviation? How we will calculate? You see, then we find the expression for this delta is I have shown here for yellow color. Means what? Mean deviation delta means the deviation suffered by yellow light. The deviation suffered by yellow light, which is known as the mean light. Means this wavelength for red light, the extreme is red light and violet. Yellow color light is considered as the mean of the wavelengths of the two colors red and violet. So that's why I am taking this as a mean deviation. The deviation produced by yellow light. That's why I have shown this yellow light is delta. Okay? Why this? Because here delta means it is the mean deviation, means the deviation suffered by yellow light. Here delta is the mean deviation, that is the deviation suffered by yellow light, which is considered the mean deviation. Okay? So this is for delta. Now as you know, delta V minus delta, that already you have derived in terms of what? Refractive index. So if I write this dispersive power omega, that is omega equal to what is delta V minus delta? Mu V minus mu R into A in terms of refractive index, already you have derived, divided by delta means the mean the deviation suffered by yellow light, means I can say that is equal to delta is equal to, this is the mean refractive index, the mean of the refractive index of the material for the yellow light, refractive index of the material of the prism for yellow light. So mean refractive index minus 1 into A, that is for delta. So this is for white. Mu is the mean of the refractive index, means for violet and red we can write mu V plus mu R by 2, that is the mean. Okay, delta is equal to mu minus 1 into A. So this A get cancelled, so I can write this as a mu V minus mu R divided by mu minus 1. This is the dispersive power. Clear? So here we have considered what? This mu is the mu V plus mu R by 2. Means the refractive index of any material for yellow light, refractive index for any material, refractive index of any material for yellow light equal to the mean of the refractive index. Mean of the refractive index for what? The violet, two extreme, one is violet and red light. Clear? And another thing you remember here, the dispersive power depends only on the dispersive power depends only on the nature of the material. This mu comes why? Because of the nature of the material of the prism, right? And it is independent of the angle of prism. It does not depend on angle of prism. Clear? And remember another thing is that the dispersive power is a dimensionless. Dimensionless. It is a dimensionless. Clear? Quantity. So it is a dimensionless quantity. And it has no unit. Clear? And dispersive power is constant for any two colors. The dispersive power is constant for this material of the prism for any two colors like your violet and red. Clear? And the another thing, remember another thing is that the greater the dispersive power of a material, greater is the dispersive power of the material, means larger is the spread of a spectrum produced by the prism. It is a larger is the dispersive power, means the spreading will be more. The spreading will be more. The angle of deviations will be more. Its ability is more. So that is the dispersive power measurement gives us this idea. And the dispersive power of a prism is positive because the dispersive power is always positive. Because what? The refractive index of the material of the prism for violet color is more than the red color. And remember one thing is that when you are calculating the dispersive power, generally the refractive index for violet color we are not considering practically, because the wavelength of the violet color is very small and it causes harm to our eye. So practically we are taking this. Red light is the extreme color, but here in the violet, in place of violet, we are taking the blue color. We are taking the blue color. So generally we are taking this as a blue. So omega equal to, when for calculation purpose, to calculate the dispersive power, we are using the refractive index for blue minus refractive index for red by mean of refractive index of blue and red minus 1. That is the formula. Clear? And the dispersive power of one of the example you can say flint glass prism is greater than that of crown glass prism. If it is a flint glass prism, its dispersive power is more compared to crown glass prism. Clear? So this is all about the dispersion by a prism. Okay? Dispersion and the dispersive power, and how we calculate the angular dispersion and dispersive power. Thank you.